Good shape there. All right, we should be ready to rock. All right, if you guys have any questions, just like the previous modules, go ahead and type them in, assuming you're watching this live. Obviously, if you're watching the recorded version, then you can't type questions in. But you can. Maybe someone on YouTube will answer them. Maybe me. So this is our fifth module. We did fundamentals of heat pumps. We did split systems and packaged rooftop units. We did small systems like ductless and VRF and so forth. We did hot water hydronic systems, and then now we are doing cold water hydronic systems. This is the shortest of the modules, but that leaves us a little bit extra time for random questions at the end. But we'll get through all of this stuff and just ask stuff as we go. So we'll do a little bit of discussion about chilled water systems and what they are, not nearly as much as we did on the heating side, because honestly, from a water perspective, from a hydraulic perspective, boiler systems and chiller systems are the same thing. Moving water around a building, right? So you have all the same things we talked about last module. You have expansion tanks, you have circulating pumps, all air separators, all that stuff exists with the same kind of logic to it. But obviously, we're making cold water in this case. And there are several different ways that we can make these into various kinds of heat pump systems. Is my clicker not working? Oh, there we go. So first thing we got to figure out is if our existing building even has chilled water, because if it doesn't have chilled water, then we're back on a different discussion. We're back to module 2 to find our solution. So we have to go, just two places we can go, obviously. We can go look for a chiller if you know what you're looking for, or if we're already looking at a particular zone of a building, a particular tenant space, we'll look at the air handler, because you may be looking at just one floor of a building, of a 20-story building, and you don't know if each floor's got a condensing unit outside or if there's one big chiller plant for everybody. And you may not have access to the roof and things like that, but you will have access to the tenant you're working with, hopefully. So you're going to look at the air handling system. Right, we talked about this before. This is the device that moves air around the building. So we got supply fans, sometimes return fans, ventilation dampers, exhaust dampers, filtration, and then most importantly for today's discussion, we have the cooling coil, and you're probably gonna have a heating coil as well, right? So that cooling coil is going to be an indicator to me if it's a chilled water system and being fed by cold water. Typically 44-degree water goes out to the coils. 56-degree water comes back, historically speaking. Not every job's that way. Or it's going to be a DX coil, meaning it has refrigerant in it. So just like before, we said you can look at the coil to figure that out. If it's chilled water, the water will come in. It'll come in, like we said, typically at 44 degrees. It'll flood this header up, send water up and down the coil, up and down the coil, up and down the coil, all these different rows, and go back to the return header and leave at 56. But if it's DX, direct expansion, meaning there's refrigerant in the coil, then instead of having a header like that, you'll have all these distribution tubes. And this one happens to be a 2-circuit coil, right? So there's a supply and a return for each of the circuits. So instead of one big header, you'll see all these little skinny distribution tubes. And that's a quick visual way to know if you have refrigerant in the coil or if you have water in the coil. And if you have refrigerant, you're going back to module 2 for your heat pump solutions. If you have chilled water, then you're on this module. And just like we said before, be careful because the hot water coil looks exactly like this one, right? You need to know if it's chilled water or hot water. Ways to figure that out. One, if it's chilled water, it'll have a condensate pan under it to collect moisture. Hot water coil won't need that, although they could have put one there, but it's not likely they would have paid for that. They don't need it. 2, the piping system hopefully is insulated and hopefully has labeling that says chilled water or CW or something like that. And then 3, you could feel the pipe. Just be gentle when you do that, because if it's 180-degree hot water, it could be really hot, obviously. So those are ways to figure out if it's hot water or chilled water. There's probably 2 of these coils in there, one for hot water and one for chilled water. So once we've identified that we have chilled water in the air handler, now we can decide if we want to make this into a heat pump system. Our decision is going to be much different than when it was a DX system. When it was a DX system, direct expansion on the right, we just decided what to do for that particular zone. If it's chilled water, chances are this air handler doesn't have its own chiller. That happens once in a while. We have a 1-to-1 relationship with a chiller and a large air handler, but it's not common at all. More likely is you have one chiller feeding 30 air handlers, or you have a chiller plant with 3, 4, 5 chillers feeding a bunch of air handlers or small fan coils or whatnot. So then your decision process is a little bit different. You will not be converting it over zone by zone. You'll be converting the whole building over at one time. So we have several different options on what we can do in this regard, and it depends on the kind of building and what we're doing. We have what I'm going to call a heat pump chiller. Just like last module, I said heat pump boiler, and I don't think that's really a thing. I don't think heat pump chiller has really been a thing either. I think people just started saying that in the past, I don't know, 15 years or something. So it's kind of a newer term, and it's not consistent. Even on this screenshot I did, they were calling it air to water heat pump. All right, so that is what most of us would call an air cooled chiller. That's a heat pump, air to water heat pump. Remember on module 1, we had air to air, water to air, water to water. This particular one is an air to water heat pump. We could also have a water to water heat pump that is a chiller. The one in the upper left there, that particular brand, at my office, we've been using that for 15 years. It gives you an idea, 12 years. It gives you an idea of how long some of this stuff has been around. That manufacturer used to just make chillers. And then one day somebody asked about heating, and they just decided to make a reversing valve in there. It's literally that simple. I mean, obviously there's more than that, but conceptually it's just you're adding a reversing valve, just like we did on the regular, small residential heat pumps. Just add a reversing valve, and all of a sudden this thing can flip modes and swap its evaporator and its condenser's jobs. So that's what this thing does as well. And they developed that pretty quickly. That manufacturer only does small chillers. They just do like 5 and 10 ton systems, or they'll bank a couple together to get 20 tons. If you're going to have a bigger project, you're not using that manufacturer. But there are several manufacturers that have this kind of stuff. There's a few on the screen here. I'll show you some more later. We're not trying to identify specific brands in this course, just letting you know that there is a volume of them that are available out there. Just like in the past, as you guys have questions today, just type them in the chat box. As mentioned, this module is a little bit shorter because it's the last one. Because this used to be, a one-day class, so the last module had all the time at the end for all the weird questions. So we will have time today for extra questions too. So how's this going to work? Similar to the drawing that we had last time for hot water, we have, in this case, it's an air to water heat pump. So sitting outside, I have to have my air to water chiller, my air to water heat pump. And it's going to have chilled water moving into the building and warmer water coming back. Like I said, historically, we're trying to get 44 and 56. Some jobs might be designed for 45 or 46 or 47. Some jobs may have a bigger than 12-degree spread, but something in that general area. And just like in the previous discussion, we have this term called lift, which is the temperature difference between the water and the outdoor air. The smaller that lift is, the easier it is for me to get the desired temperature you want, and the more cost effective it is, right? For example, if I want 44-degree water, right, inside, and it happens to be 50 degrees outside, yeah, it's pretty easy to make 44-degree water with 50-degree air, right? But if it's 80 degrees outside, it becomes a little more hard, right? And if it's 100 degrees outside, it becomes very hard to do that. So same kind of idea that we had before. The closer the outdoor temp is to the water temperature, the better. And just like before, we can't control the outdoor temp, obviously. So that means instead of designing for 44 degrees, if I can design this for 46-degree water, meaning my air handler coils are just a little bit bigger, that might be beneficial to me. I can't get too crazy with it like I did with the hot water. Remember on hot water, we said we're designing for 180, but if you could design it for like 120, 110, that's awesome, by putting in big radiators and big coils. I can't go that extreme with the chilled water, because in most applications, nearly all, the chilled water coils job is also to dehumidify the air, not just cool it. So while I could send 60, 65-degree water into the coil and cool the air down, a lot of 65-degree water, I'm not going to be able to hit the dew point of the air and then hence dehumidify the air. So that's not going to work for most projects. So I can bump it up a little from 44 to, like in this example, 46, but I can't be too insane with it. Oops. So that's a heat pump chiller. There's also what we call a heat recovery chiller, or some manufacturers call it a heat reclaim chiller. Heat recovery and heat reclaim mean the same thing in this discussion. These are also heat pumps, but they are a little bit different in terms of how they are utilized. Sometimes it's the same machine, but usually it's not. The difference on these is that usually they do not have a reversing valve in them. They would do their reversing work with the water valving, or they would never reverse. They would always just be in one mode or the other. So I'll give you some piping examples to kind of explain that here. But these come in all kinds of flavors. These are way more available to you than the traditional reversing valve style heat pump, because these are available in pretty much every kind of machine: air to water, water to water, outdoor mounted, indoor mounted, ones that are 500 tons, ones that are 10 tons. There's all kinds of range of these guys available. This is a pretty established thing in the marketplace. So it'll be a little bit easier to talk about some of that stuff. Both of these types of things, heat pump chillers and heat recovery chillers, have made their way into the International Energy Conservation Code. That's how you know you're big time. That's how you know you made it, is when they start policing you for your efficiency. Up until prior to 2021 code, I think, or 18. I'm trying to think of which one it jumped into. But up until that point, this did not exist. So when you put in a heat recovery chiller, you had to make it match the efficiency in the tables for the regular chillers, which was hard to do. And if you did a heat pump chiller, then you had to go pretend that it was like a small, air side heat pump and try to make it match that. But now it's actually a defined thing for both of these. When you look at these tables, and this is similar to other things in the code, I know it's a little bit small for you guys, but I'll explain it. When you look at the efficiency of stuff you have to do for the International Energy Conservation Code, which is what you in your state and I in my state follow, you go find the section that you're in first, right? Because there's like 18 pages of equipment efficiencies that you have to hit, plus a bunch of other stuff you have to do other than just equipment. But the equipment has all these different tables. So in our case, we scroll past the heat pump section. We scroll past the chiller section in the document, and we go to the very last section, which is 403.3.2.15, and it says heat pump and heat recovery chiller packages. That's where you got to get over to. We did that in this case. This is the heating efficiency table. So you do that, and then you got to figure out what kind you have. Air source, meaning the heat pump is going to be taking its energy from the air and giving it to the air, specifically the heating mode, taking it from the air. Water source, positive displacement compressors. Water source, centrifugal compressors. Those are the two kind of compressor divisions we have for regular chiller efficiency tables. So they've used those same divisions for these kind. So you do that, and then depending on that, you go look at the tonnage you have. For air source, the rules are the same for every size. For water source, there's breakdowns for little ones under 75 tons, 75 to 150, 150 to 300, and so on. And you look at it that way. So I get to the right table, I find the kind of machine that I have, and then I find my tonnage. We'll just stick up here on the air source for right now to make it clean. You have, and this is already getting more complicated than it needs to be, right? But you have path A and you have path B. And the reason you have that is because regular chiller efficiency also has path A and path B. What that means from a code perspective is that you can follow either path A or path B, one or the other. You do not have to meet both. And the reason we have path A and path B is because some applications need chillers that are very good at part load, meaning that they have all these different weather conditions going on, and you want to be able to be efficient when it's 95 degrees out, 80 degrees out, 70 degrees out, etc. Other chillers need to be more efficient at full load because maybe they're being used for process application, or maybe you have like 6 chillers going in the building and you don't need to ramp each one up and down because they're small relative to the whole building, and you're going to turn them on fully one by one. So you don't care how efficient each chiller is at part load because you're only going to put the chiller either on or off. You're either putting 100 tons on or you're putting 100 tons off. So full load becomes more important. So you get these two ways to comply, one of which is harder to meet the full load requirement. The other one's harder to meet the part load requirement. So these are the efficiencies that you have to meet on the cooling side of the equation, right? And these are very similar to what everybody does when they design a chiller plant now. And then you have the heating efficiencies over on the right. Let me clear some of my slop off just for argument's sake. So you have heat pump or heat recovery. So 2 different sections in here. Each of them has 4 columns. So let's say you have the heat pump. That means you're going to have a refrigerant reversing valve inside the chiller. And it's very similar to what we did before with the hot water boiler and so forth. In fact, that hot water boiler that I described in the last module, it would have to comply with this table too, under this heat pump heating efficiency. So that you got that, and then you have to define the conditions. So if it's an air source one, which we're talking about, you have to meet 2 efficiency levels. You have to meet this efficiency on a 47-degree day, and you got to meet this efficiency on a 17-degree day. 47 and 17 are the 2 testing points that pretty much all heat pumps use for outdoor air temperature. That's why they're using it again in this table. You have to meet both of those. So over here on the cooling side, you got to meet one or the other. On the heating side, you got to meet both of these things. This is all designed to make it very confusing for you. Then you got to decide what leaving water temperature you have. So on these tables, you have 105, 120, 140. And then there's this weird boost thing, which nobody really understands what that means. But in any case, you're not doing that typically. You're designing for 105, 120, 140, or higher than 140, obviously. And you got to be a certain efficiency. And the lower the water temperature, the more efficient the chiller has to be, because they know you could be more efficient. If it's an existing building and you're trying to meet the old demands where the building was designed for 180-degree heating water, then you're probably going to go ahead and design the building for 140, right? Because that's probably about the most you can get out of a heat pump. And that's the way it's going to go. If it's new construction and you could design the whole thing for 120, great. And if it's like radiant flooring systems, then you'll design the whole thing for 105. That's why you have these 3 numbers here. And then if you have a heat recovery chiller, which means you don't have a reversing valve inside the chiller, you're going to reverse things on the water side, or you're going to be running simultaneous hot water and chill water, which is mostly what you're going to do. Then you'll be in this other column, and it works the same way. There's nothing in there for the air source side because you won't have this on the air source side. You'll be doing this only with water-to-water chillers, because the condenser water loop and the evaporator water loop have to switch jobs. So they both need to be doing water. I realize I just talked a bunch of stuff there and rattled it off. If you guys have questions, please ask them. And then if we were in the water source section, which I won't go through that in detail, it would work the same way. The only difference on how that would work, other than me picking the tonnage, is that I would also on here tell it what water temp I'm designing for. And 4454 is going to be the closest one that I'm going to have. That's what the machine's going to be typically rated at anyway for most chillers. All right, moving on. So let's look at a piping schematic for a traditional water-cooled chiller plant. Obviously, every plant's different, but in this particular example, we have 3 indoor cooling coils. So let's just say they're air handlers. It could be 3, it could be 50, it could be 100, it could be 1, but we got 3 in our example here. We have 2 chillers in the chiller plant. It could be 1, it could be 2, it could be 9, but I got 2. 2 is probably the most common scenario. It's not super common to have just 1 chiller, because then if something goes wrong and you got to fix the machine, you got to work on it for a day or 2, you have no cooling in the building, right? If you have 2 chillers, you have some level of redundancy. If one chiller's down, the other chiller can cool the building. And if it happens to be the hottest day of the year, at least the other chiller can half cool the building. All right. So that's much more common. And in this case, these 2 chillers are connected to 1 cooling tower. It could be that each chiller has its own cooling tower, or in this case, 2 chillers are sharing 1 cooling tower. Each chiller could have 2 cooling towers, so you'd have 4. There's all kinds of combinations of these things that you can do. So in reality, what happens on a chilled water system is you have 2 separate unrelated hydronic loops. I shouldn't say they're unrelated. They're related by the chiller, but pressure-wise and hydraulically, they're unrelated to each other. So I have these 2 chillers over here, and let's just draw a dividing line. I thought I clicked that. Right here, everything to the right of this is the chilled water side, chilled water. And everything to the left of this is the condenser water loop. And those water loops don't touch each other. The water doesn't mix. They're separate. So these 2 chillers each have their own circulator in this case. And that's not always true, right? But it's usually true. And these guys are taking water. They're shoving it into this water loop. And this is a primary secondary arrangement. So these guys, their job is to keep making this circle of water. And then if the other guy turns on, he makes that circle of water. That's what they do. And then this loop over here, which is the same water, is the secondary loop. So what those guys do is, as these zones need more water, they turn on 1, or in this case, 2 parallel circulators. That's for redundancy reasons, kind of like the reason you have 2 chillers instead of 1 in case one goes down, 2 circulators instead of 1 in case one goes down, or if it's really, really, really hot, you might run both. right? So when they turn on, they suck some of the water this way. If they're off, the water just goes around the loop because this circulator is pulling the water back in. But if these guys turn on, either one of them, instead of the water going down this bridge, they go out to the building, right? This primary loop is just in the mechanical room, right? It's short. It's like 30 feet long. And then the rest of this is, hundreds of feet long. That's a pretty common scenario for both chillers and boilers to have that primary, secondary. We also have systems now that have, we call them variable primary, right? So on this one, these are old school chillers, and these circulators down here probably run at a fixed speed. They just turn on and off. The chiller's on, circulator's on. These ones over here are variable speed, which means I got a pressure sensor out here somewhere that's measuring the pressure and maintaining it with these circulators. You could also have variable primary, which means you don't have two loops on the chilled water side of the equation. What that would mean is that these circulators right here do the whole thing. They are sized to handle whatever these chiller needs. Or you can think of it as these two do the whole thing. So like these guys would be gone, and this bridge would be gone, or might have one for just low load conditions. But conceptually, it's gone. And these circulators would be sized to handle the whole building. And you would vary these. Some chillers can handle variable water flow through them. Some chillers cannot. Same thing with boilers. So that's why we have variable primary for chillers and boilers that can handle it. And we have primary, secondary for machines that need a dedicated flow through them. So that's what's going on the chilled water side. And then each of the air handlers or fan coils or radiant ceiling panels or whatever you have, each of those guys has a control valve on them. And the thermostat for that zone or the building automation system for that zone is going to open and close that valve more or less to allow more chilled water to flow through the coil to cool and dehumidify that air. And then typically the last zone will have a three-way valve. So these guys are two-way, this guy's three-way. The reason being is these are variable speed loops and they're going to control the pressure sensor. If this guy shut off completely, there'd be no flow through that loop and the pressure sensor wouldn't be doing a very good job. So a lot of times we'll have a little bypass loop at the end, just so we have enough flow through the total loop that we can measure something. All right, that should be the chill water side. The condenser water side on the left over here, that's a separate water loop. So the water in these pink and purple pipes never touches the water in these red and blue pipes. It's totally separate. Inside the chiller is my refrigeration cycle that we talked about in module 1, evaporator, condenser, compressor, expansion device. But instead of being like your house where I have a condenser coil outside and evaporator coil inside, and those guys just switch jobs, now I have a water-based condenser coil in the chiller and a water-based evaporative coil in the chiller. So there's two heat exchangers. One is water to a refrigerant, and the other one's refrigerant to water. So these guys, they take heat out of, these air handlers take heat out of the air, right? Remember we said we had pretty standard to have 44-degree water going out and 56 or 55 or 54-degree water coming back to the chiller, right? That's what he's doing. So these coils are sending me cold water. I'm adding heat from the space to the coil, and I'm sending warmer water back to the chiller. And the chiller's job is to cool that water down with the refrigeration cycle and send cooler water back. Once it removes the heat from the water to send cooler water back, now it's got this heat from the water that it has to do something with. It uses the refrigeration cycle to change its pressure like we did in module 1 to boost up the pressure higher, which boosts up the temperature, which allows me to reject the heat to a warmer water loop. So this condenser water loop historically is providing me 85-degree water, and I am sending him 95-degree water back. It doesn't have to be these numbers. These are just the 4 standard numbers you typically would see on a historical design. So once again, I'm cheating by moving heat from a cool area to a hot area. I'm cheating physics by using the refrigeration cycle and boosting the pressure. That allows me to take that heat and shove it into this relatively warm 85-degree water, and hence the water warms up to 95. Then we send that water outside. So here's the roof of the building. Actually, these circuits are probably inside the building. So here's the roof of the building. We send this water outside. We have to have all the same components we had over here. So we have to have a circulating pump. We have to have water strainers and those kind of things over here. We send this water out to the cooling tower. And then for most cooling towers, we take that water and we mist it into the outside air, and we blow air across it, or we suck air. In this case, it's a draw through. We suck air across it for this particular design of cooling tower. And when we do that, that has a cooling effect on the water. Kind of like if you've ever been swimming outside and you step outside of the pool and you're wet, it's 90 degrees outside, but a breeze comes, you feel cool. how the hell are you feeling cool when it's 90 degrees outside? Because you're soaking wet, and that has an evaporative effect. It uses that heat from your body to evaporate the water, and the airflow speeds all that up. Well, your body gives up a ton of heat when it evaporates water. So sweating is your body's mechanism is your body's fourth mechanism, your last resort to get rid of body heat. And it's really effective, but you have to keep drinking more water. And just like when you have to keep drinking more water for your body to keep sweating, this cooling tower has to keep drinking more water, right? Some of that water is going to evaporate into the outdoor air, right? So this air coming out of here, it's going to have a bunch of heat, but it's also going to have a bunch of little water droplets in it too, right? It's going to be pretty moist. And that's when you see like a plume of smoke coming off a cooling tower. It's not smoke, it's condensation. There's no fire in there, there's no combustion. So it's condensation coming off, but it looks kind of like smoke. So I have to keep adding more water to this. So I do have to pay for some extra water on this kind of system, but it's really efficient. Electrically speaking, it's way more efficient than an air-cooled chiller would be. So you're trading off the cost of electrical energy for the cost of water energy. And depending on where you live and how expensive water is, one or the other might be a better deal. And then if you get to very large buildings, right, high rises, like, 100 stories and bigger and stuff like that, you're not going to have the space to put air-cooled chillers. You're going to have to do cooling towers. So at that point, the cost of water is irrelevant because you can't do anything other than this. All right, so what that guy does is take my 95-degree water, evaporatively cools it, and sends me 85-degree water back, where I can now use the refrigeration cycle in one of the chillers to keep dumping more heat into it. All right, hopefully this is making sense. All right, so what the interesting thing comes in is that I have chillers like this. I'm saying the industry has chillers like this running all over the world, and they're running in all seasons. So like I told you guys before, I live in Illinois, only like an hour from Chicago. In Chicago, there are hundreds of buildings that have chillers like this with a cooling tower that are running this cooling tower in the middle of winter when it's like 0 degrees outside, right? Big buildings run cooling year round, no matter what. And you guys are the exact same way. Maybe not if you're out in the suburbs because you don't have any ginormous buildings, but if you're in Boston, you have these ginormous buildings. Any building, if you look at it, I don't know if I did this on module 1 or not, so I'll just briefly talk about it now. On the building, if you are the interior zone, this is you. You look really good today. Have a good Friday. If it's 0 degrees outside or whatever temperature, okay, great. This zone right here is warmed up to 72. They got the heat going wherever they got, 72. This is 72. This is 72. This is 72. All the perimeter zones got their heat on because it's 0 degrees outside and they have full glass windows. So they're all 72. So if this isn't me in the middle, I don't know it's 0 out. I think it's 72 all around me. All 4 sides of my zone, it's San Diego. It's 72. And the floor above me and the floor above me, everybody's 72. So how much heating do I need? I don't need any heating when it's 72. I'm good, right? So I need cooling still. I need to cool my building down because I have lights, people, computers, all that kind of stuff going on. I got to get rid of that heat. So the interior zone of a larger building needs cooling year round. So we run these chillers year round. Well, obviously that's kind of wasteful. Like, dude, you're going to run a chiller year round and you're just going to just throw the heat into the air. Like, dude, it's kind of crazy, man. I get it when you do it in the summer. What else are you going to do? But in the wintertime, you're just going to take perfectly good heat and throw it into the air. And then somewhere else, there's a boiler running the heat. That's ridiculous, right? And that's going to be where this heat reclaim chiller comes in. So by energy code, you have to start recovering energy from that condenser water in those kind of winter times, right? So this is the same kind of idea, just a little better drawing. We got air handlers with fan coils over here, right? We got our pumping system. This is all of our chilled water loop over here. This is a primary only loop, not a primary secondary. I got 3 chillers in this case, right? Instead of 2. But what I'm going to do is recognize the fact that, hey, I'm going to run this chiller plant in the middle of winter. I don't need all 3 machines, but I need 1 machine in the winter, right? Because I don't have a lot of cooling to do. I only got to cool the interior. I don't have to cool the exterior. That's heating season for those people. So I got to cool the interior. But instead of sending my water out to the cooling tower to just waste the heat away, the energy code says, and this is when you're above a certain size, right? It's not every system, but when you're above a certain size capacity of your system, you have to put a heat exchanger on that condenser loop and try to save that energy. So instead of rejecting all the BTUs out into the sky, you reject as many BTUs you can into this heat exchanger. And this heat exchanger can be used to heat your makeup or to heat your service water, your domestic water, right? Because somewhere in this building, I also have hot water heaters or boilers heating up that water for the showers and the sinks and all these different things. Instead of heating those with electric heat or with a gas-fired burner, why don't I heat them with this heat that I was just about to throw away into the sky? It's free energy at that point. Once I've decided to throw it in the trash and just expel it into the sky, it's free energy to whoever wants to use it. And guess what? My domestic water system wants to use it. So I have to reclaim that energy to do that. And you can certainly do this. And it does save some energy. It's not as much energy savings as you would think. Like conceptually, you're like, this is the way to do it, dude. I'm throwing X amount of BTUs in the sky. F it, man. I'm going to throw those BTUs into my space. However, when you do this, the chiller operates significantly less efficiency than if you just dumped it into the sky. Reason being is that this hot water surface makeup water, it's coming in much cooler than this water would have been coming at, like in the summertime, right? In the summertime, my chiller is expecting to get 85-degree water delivered to it by the cooling towers. And that's what they're all designed and selected for and all that great stuff. But if I'm going to use this as makeup water for my service, my domestic water coming from the city in the middle of the winter, it's probably like 50 degrees, right? So this is 50-degree water coming in, right? So now my chiller has to dump its heat into, can't even say it. I don't know what the word is. I lost my wording. That hardly ever happens. Maybe to regroup myself, I'll just read what it says on the slide. The heat exchanger captures the condenser water heat, which is waste heat, as we said, from the 85-degree water. But this is where I was going with it. The higher leaving water temperature that I'm trying to make with this guy is going to be increasing the chiller lift, and that reduces the efficiency. Remember the lift was the difference between the water temp, right? The water temp and the outdoor air, right? If I'm trying to make warmer water, this is going to penalize my lift, which penalizes my efficiency. So I do save energy compared to doing nothing, but I don't save all of the energy just straight up as if I thought I was going to save. So we have a couple solutions to that involve what I'm going to call it a heat pump chiller or heat recovery chiller, heat reclaim chiller. HR in this case means heat recovery or heat reclaim. So what I'm going to do, same idea. I got all these air handlers over here on the chill water side, right? I got my two chillers, got my cooling tower. Instead of adding a heat exchanger on this water and then sending it over to my domestic water, I'm going to add a chiller onto there. Okay, that's okay. That sounds interesting. Are you a chiller salesman, Ryan? I am not. Other people in my office are, so maybe they like it because of this. But I don't care what people buy. I'm going to add this chiller on here, and I'm going to specifically have this chiller be different than these other two. This is going to be a heat recovery or heat reclaim chiller, a chiller that is specifically selected. It's the same components, evaporator, condenser, compressor, all that stuff, but it's specifically sized and selected to extract heat out of this loop and put it into that loop, right? So I'm going to use another refrigeration cycle to do that. So what's going to happen in this case, let's say this is wintertime. I can go ahead and shut my other machines off. I probably don't need a lot of cooling over here. Some of my zones need cooling, right, for their interior zones. I'm going to run the heat reclaim chiller. And this guy is going to send water out to them and take water back, right? But instead of being designed for a cooling tower, he's going to be designed to operate with the kind of water temperatures you need for your heating load. So this chiller is going to take the place of your boiler or your hot water heater. So this becomes extremely useful in places where you have year-round, no, I shouldn't say year-round, almost year-round need for simultaneous hot water and chilled water. If your building only needs chilled water in the summer and you only need hot water in the winter and you don't have any overlap, then fine, you don't really need this. Or if you only have 1 or 2 months of overlap in the spring, you don't need this. But if you have year-round need for hot water, for example, that building I mentioned where the interior zone needs cooling all the time, and then you have boilers that are, maybe it's a hotel or something, and you got boilers that are doing water for showers and laundry and all that. You need hot water all the time. Or maybe it's a high school, right? And you need chilled water to cool certain areas. And then you have the swimming pool that needs heat all the time. These kind of things where you have a lot of hours of overlapping heating and cooling needs. That's where this heat reclaim chiller would come into play. There's different ways you can do this. So this one is in parallel. So what that means, I haven't got any questions yet. So that either means I'm awesome at explaining all of this, or you guys are bored with it. But this one's in parallel, meaning that there's this flow path, or that flow path. They're all in parallel to each other. The water molecules coming back could go any one of these 3 parallel paths. So I added this heat reclaim chiller in parallel with the regular chiller plant, which could be 1, 2, 3, 4, 5 chillers. So he's in parallel. This guy is going to be piped to the chiller plant that way. He's going to be sized for the heating load. What does that mean? Right? You're going to get a chiller and you're going to size it for heating, right? So for example, let's just make up some numbers. Let's say this guy is a 500-ton chiller. This guy's probably a 500-ton chiller because nobody likes 2 different size chillers. They like to put 2 identical ones in. That way, if you ever need to grab a part off of one to get the other one up and running or something, you can do that. And it makes everything really balanced if you switch between the two. It's very rare that you would see one that's 800 tons and one that's 200 tons in order to get your 1,000 tons. So I have 500 and 500. And then this chiller down here is sized for whatever the heating load is. That could be domestic water, showers, laundry for like a condo or apartment building. It could be swimming pool stuff. It could be an office building where I got to heat the perimeter. Right. So whatever my hot water load is there, and maybe that equates to 300 tons. Right. And that guy will be sized for that. And he'll be running for that. I'm going to size this for the baseline heating load. So maybe the whole heating load on the worst case scenario day is 603 tons of heat. But on the least amount of days, it's going to be only 300. I'm going to size this guy for 300. And I'm going to let him just put all the hours I can on that. He's going to run year round, nonstop, just shoving heat from this guy to that guy. Because I always need 300 tons of heat. And I always need whatever, 3, 4, 5, 600 tons of cooling over here. I'm going to size him for whatever that simultaneous overlap is. So maybe this 300 tons represents my domestic load, right? Showers and hand washing and laundry, and maybe at the hospital, and they have all kinds of needs for hot water and stuff like that. And then it could need more hot water for heating the perimeter of the building, at different times of the year. But what's my baseline? What's that? So that's what I'm going to size it for. So this guy just constantly shoves heat between these two things. You want heat, you want to get rid of heat. Perfect. Let's marry you guys up. Right? When I control this system, I'm going to control this for chilled water. What does that mean? That means somewhere in here, I have to put a temperature sensor in the water piping that says how much to ramp this chiller up and down. It's going to be, variable capacity like everything else is. So somewhere in here, I'm going to put a temperature sensor, in this case on the chilled water side, and I'm going to say, hey, dude, make me 44-degree water. And whatever heat you have, instead of sending it to the cooling tower like these dudes do, you're going to send it over here to this heat exchanger. It's going to heat up this boiler water or whatever it's going to be. The next way I could do this would be putting them in series. What does that mean? So this is the same thing, same 3 air handlers over here, same 2 chillers, same cooling tower. Everything's the same right now. And instead of putting a chiller in parallel, I have one in series. What that means is the water coming back from the building gets pulled off that loop. It gets cooled by my heat recovery chiller. Then it gets put back into the same loop and then goes through one of these 2 chillers, right? So it's in series. It goes from one into the next one as opposed to side by side, right? So in this case, it's piped a little bit different, obviously. And his job in life, this chiller job in life, is to take load off of those 2 other chillers. That's what he's trying to do. He's trying to basically pre-cool this water down. So I got whatever temperature water coming back, right? Say 56 degrees. And this guy's job is to get me down to whatever, let's say 50-degree water. Then these guys start with 50-degree water and take me down to 44-degree water. So what happens on these guys is they have lower lift because they don't ever see the 56. They only see the 50. So they're going to be running more efficient than they would in a regular project. So I've made these 2 more efficient by this guy doing some of their work from up at the front. And I've taken the heat from this water loop and I've sent it over to whoever wants hot water in my building, right? So you can do this with a chiller or a water source heat pump. Once again, these big chillers are really just water source heat pumps. You will seldom find them labeled that way because the manufacturers of chillers and the guys who design it and the engineers that work on chillers, they are very prideful individuals, and they don't want to consider themselves to be anything other than a chiller. They're a chiller, right? We just found a way to use our chiller to heat your building, right? So it's still a water source heat pump. It's just a really big ass one. Sorry, I didn't mean to swear. But they're probably going to be labeled and marketed and sold as heat recovery chillers or heat reclaim chillers, but they are in fact the same thing as a water source heat pump. So it's piped onto the chill water line, like I just mentioned. It's once again sized for this heating load. just run them all the time for whatever the baseline heating load is. But in this case, now I can control it to a hot water set point instead of a chilled water set point. What does that do for me? So instead of controlling it to maintain 44-degree water like this guy maintained, because that 44-degree water had to go out to the loop, and I can't start sending these air handlers, hot, warmer water. They need their 44, man. That's what they're sized for. Here, I don't care what temperature the chilled water is. I got 56 coming back. If this chiller barely is so tiny compared to these guys, and all he does is cool the 56 down to 54, cool. That's 2 degrees free cooling that I just got for the other guys. It's going to be waste cooling now instead of waste heat. In this case, I'm taking the waste heat and I'm using it to heat something else up. In this case, I'm running this chiller as a heater to heat this water to maintain whatever 130-degree water going out to this load. And I have waste cooling over here. It's kind of a different weird way to look at it, but allows me to control the heating load more precisely. This is probably a slightly more preferred way to do this for most people's applications, especially if this chiller is small relative to these chillers. If they're pretty close to being equal in size, then this way is probably going to work out a little bit better. But if this is like a little tiny pony chiller and it's only doing a couple 100 tons, let's say it's doing 100 tons of cooling on a plant that does 2,000, this is probably a better way to do it. All right. The third way we could pipe this up, looks like we got a question. All right, let's see if this question is something that I did to confuse someone. Where's it at? All right. Khalid asks, what is the baseline load that the heat recovery chiller was sized for goes to? What happens? What happens if the base load of the chiller goes significantly lower? Where would the extra heat go? Right. So in this particular example, let's do both of them for your question. In this particular example, let's say that I size this for, I think I said earlier, 300 tons. And let's say for some reason it's a holiday weekend, whatever. So this, or it's not a holiday weekend, it's something else, and the hotel needs less or whatever. And it goes down to 200 tons. For whatever reason, it's 200 tons instead of 300 tons. This chiller would then have to ramp down. Right. And that's okay in this case. He ramps down. And instead of giving me X degree water, it's something slightly warmer. In this case, if this load gets dropped down, this guy would also have to ramp down. But now the problem is, hey, this might have been my only source of cooling running for this guy. Now somebody else has to kick on to make up the difference, assuming I still have the cooling demand. This doesn't happen a lot because if your heating demand is lower for the building, right, meaning you're using less domestic water and stuff like that, probably means there's less people there, which means you need less cooling. So kind of they usually go up and down together for these simultaneous loads, but not always. So in this parallel arrangement, if this chiller needs to start staging down because this load is so low on the heating side, that means that somebody else has to come on and take care of this cooling. In this case, I'm always having someone else come on. This guy's always sending water to them. He's super small compared to these guys. So these guys don't even really barely notice it. They'll ramp up slightly, but it's not like I have to turn another machine on. It's already on, right? So these chillers can still be variable capacity chillers over here and heat recovery, and they can ramp down if your load goes lower. But it doesn't really make a lot of cost-effective sense when you do that. I don't want to put in a 1,000-ton chiller that's going to almost always be ramped down to 300 tons and hardly ever need more than that, right? So I don't want to size it for my cooling load. It's much cleaner to size it for the heating load. And if you notice that size for heating load, these chillers are a little more expensive than a regular chiller up front because you have a little more controls. So I don't want to size it bigger than I need. So typically you size it for the baseline, but it can in fact ramp down. And then if somebody still needs their full amount of cooling, one of the other chillers has to ramp up. If you happen to have a weird scenario where, hey, I got this building, Ryan, and they always need exactly 300 tons of cooling and exactly 300 tons of heating, can I just put a heat reclaim chiller in and put no other chillers in this and just have that one guy just shove heat between these two places? Yeah, you could do that. But the problem with doing that is that what happens when it doesn't actually end up being exactly the same loads? There's nobody left to make up the difference. So in that scenario, you'd have to size it for the higher of the two loads, right? So say it was 300 for cooling and 250 for heating. You'd size it for 300, knowing that you had too much capacity, or you had more cooling capacity than heating capacity. So you'd still need a cooling tower to take care of the other 50 tons. Or it could be the opposite. Let's say you need 300 tons of heating and 250 of cooling, right? You could just not buy a cooling tower, put all the heat into the hot water loop, and then you need a boiler to give me another 50 tons of cooling. If you've ever done a water source heat pump job, right? These are typically downtown high-rise type buildings will have these. Each tenant will have a water source heat pump in the closet, which means they have a machine that takes water in, and it has a refrigeration cycle in it with a compressor and everything, and it makes warm or cold water, a little heat pump in there. And instead of dumping its heat to the outdoors like a residential heat pump, it dumps its heat into a water loop, and that water loop goes around the whole building. The cool thing about those water source heat pumps for individual tenants like that is some tenants can take heat off of that loop, and different tenants can put heat onto that loop. So if you're in the interior, you're dumping heat onto the loop. And if you're in the perimeter in the winter, you're taking heat off of that loop. And if I take 2 tons of heat off and you add 2 tons of heat, I don't got to run a boiler or a cooling tower, right? It's just the heat pumps that are running. And then that water loop is just a circulating heat between zones that want it and don't want it. And you still would have a cooling tower or boiler in the building, because if it didn't line up, like, oh, I took this much heat out of the loop, I only put that much on, the boiler's got to kick on and temper the water back up to something reasonable, or a cooling tower has to trim it off. The same thing could happen if you had this chiller plant set up that way. The cooling tower has to kick on to trim the difference, and when these two guys don't match, and the regular boiler or hot water heaters have to kick on to trim the difference when these two guys don't match. All right, hopefully that answers that. I mean, to answer your specific question, if the cooling tower, but we have asked where the extra heat goes, it goes to the cooling tower, right? Via these other chillers kicking on in this example, right? In this example, I have to be able to use all the heat, or this guy just has to ramp down completely. All right, the third way is to have redundant chiller in series. So this one's going to control the hot water set point also. So the 2 hot water set point ones, I like those better. So he's going to say, hey, I want to make 125-degree water, or whatever you designed it for. Make me that water. I'm going to have a temperature sensor in the pipe to do that. And this guy's going to run to maintain that water to give heat to whoever over here wants this amount of heat, right? In this case, though, I have these 2 chillers in series, and I'm probably going to put them in series counterflow. And that's a whole nother class. But what series counterflow means, I don't know if I could draw it. I should have put a slide on here. Series counterflow means I got my chilled water coming into one chiller, I'm going into the next chiller, going out to the building, right? And then the condenser water comes in, and it's also running through those same 2 chillers in series, but it's counterflow to the other 2 machines, to the other flow. So the chill water is going this way, or the condenser water is going that way, and the chill water is going that way. That means the coolest condenser water gets to do work on the coolest chilled water. And this is a pretty efficient way to run 2 chillers in series. In fact, if you're putting any chillers in series, you should probably put them in series counterflow. Stop putting them in just straight up series. It's not a very efficient way to do it compared to series counterflow. You can typically get an extra 10 to 15% efficiency for series counterflow versus over straight series. So whenever we have chiller plants that we already have in series counterflow, or we want to design them into series counterflow on purpose, we'll pretty much set it up this way. All right, so differences on this one versus that one. This guy's piped into the chill water line just like the other guy was. I'm controlling it based on the hot water set point, right? But over here, I was sizing the chiller for the heating load. And in this case, I'm sizing all these chillers relatively equal to each other, so I can kind of control them in a similar fashion. It's not a ton different than the last one, but it's a little bit different in the concept of it because I can flow the water a little differently. These are different ways that you could pipe these guys in. In terms of the water temperature, kind of like what we talked about on the heating side for heat pump boilers, these heat recovery chillers and heat pump chillers have a similar scenario. Depending on the outdoor air temperature you want or you need to operate at, you're going to be challenged to get certain water temperatures. So if it's only 0 or 7 degrees outside, it's really hard to make 140-degree water with some of these machines. I may be only to make on some machines 105-degree water, right? That doesn't mean it's a bad idea. It just means somebody else has to help me heat it. So I might be taking that 105-degree heat from the chiller and using that to preheat my domestic water, which is coming in from the city at 50 or 55 or 60 degrees. But then maybe the boiler has to take the 105 and heat it up the rest of the way for me. I'm still taking load off the boiler. All these heat recovery machines are taking load off of the boiler, and they're using waste cooling to do it, which is fantastic. Where I live, our electric utility is not the one paying rebates for these projects. It's my gas utility. Where I live, it's separate. The gas utilities are not connected to the electric utilities at all. The gas utilities are the ones that will pay a heat reclaim chiller rebate. And you're like, you guys are paying a rebate that doesn't even have a gas connection to it? And they're like, yeah, because you're shedding load off of the boiler or the hot water heater. So we're all about saving the gas. That's our goal. That's our mission. That's what the state requires us to do. If we save gas by reclaiming waste heat, we can do that. Now, they're not allowed to save gas by using electricity instead, but I already have to run electricity to cool these systems. So I'm already doing it. Like the electricity is being bought to run the cooling plant. Now I have this waste heat. If I can use the waste heat to unload the heating gas plant, that's where they can pay a rebate. But in any case, the warmer the water you make, the easier it's going to be to heat the space. So if it's 47 degrees outside, I could pick any of these water temps and they all could pretty much make me nearly the same amount of BTUs, right? But as the water temperature drops, I mean, I could still make 140-degree water on a 32-degree day. It's just I'm only be making this much of it down here instead of somewhere up there. But for all of these, like we showed before, it's going to be dropping off. This graph might do a little bit better job of it. This is outdoor air temperature from 50 to 0 degrees over here, which is, 5 degrees is probably your guys' design day, I think, when I looked it up. Where I live, it's 0 or 1 degrees. Actually, where I live, it's -5, but in the Chicago area, it's like 0 or +1. COP, coefficient of performance, like we said before, like 3.5 is 350% efficient, right? This dotted line here is what many people will utilize as kind of like the coefficient of performance that I need for this to kind of make some sense for amount of energy it takes to distribute electrical power to my building, right? So, and you saw that on the small split systems, we had a COP, a 5-degree COP of 1.75 was considered a cold climate heat pump. This is at 1.8 on here, but same kind of logic. If I can get above that line, I'm usually in pretty good shape, right? So 105-degree design temp for my hot water loop would crush it. It'd be awesome all the time, right? If I ask for warmer water, I'm going to be making less BTUs, right? Indicated over here, and I'm going to be making them less efficiently, right? It costs less money to make 105-degree hot water than it does to make 104-degree hot water. That's kind of intuitive, I think. So in these cases, I'll be losing efficiency, and at some point down here, it's going to be cheaper or smarter from the COP standpoint to run my boiler. Cheaper would depend on the cost of my two fuels, and that'd be a different mathematical calculation. So in other words, designed for lower water temps, which means put in bigger hot water coils and or bigger radiators or whatever you have, bigger heat exchanger for domestic water, etc. All right, a couple more slides on here. We'll switch gears a little bit. So off of the heat reclaim chiller and back to the reversible heat pump, the one with the reversing valve in it. You can do a reversing valve. I mean, I got these out of order. Hang on 1 second. This guy. Can I exit this? Oh, keep my notes. No, discard my notes. Hang on. This guy should be there. Okay. Save that. Republish. Maybe republish. There we go. All right, so this one first. It'll be more logical. All right, so I got the reversing valve inside here. So in the cooling season, I'm sending cold water out to the building. I'm dumping hot water or dumping heat outside. In this case, it's an air-cooled machine, right? I got my evaporator coil inside the chiller, my condenser coil inside the chiller, my expansion device like a TXV, or a chiller probably EXV, electronically controlled TXV, and I have my compressor on here, right? When I switch to cooling mode scenario, right, everybody just switches jobs. This is probably not the best drawing because it may look like these two flips positions. They don't. They just reroute the piping. But from a conceptual standpoint, this guy's now cooling the outdoors and he's heating the indoors, right? Just like a regular heat pump did. He's taking heat from outside running it through the compression cycle and dumping the heat to the inside. If you don't want to get a chiller with a reversing valve inside it, or the machine that you need is so large that that's not really going to be practical, there are other things that you can in fact do. And this one is showing doing the reversing valves on the water side of the equation. So instead of having reversing valves inside the chiller, they're outside the chiller. And instead of the reversing valves reversing refrigerant, they're reversing water. So actually, that's the next one. Maybe I did have these in the right order. That's this one later. Ryan. So dumb, Ryan. Okay, I'm done. Okay, forget what I said about that reversing water. I'll show you that in 5 minutes. These the drawings look very similar, and I was down that path in my brain. This one is one that has a reversing valve on the refrigerant side. So I apologize. There is a reversing valve on the refrigerant side. In this case, there are 2 air-cooled chillers on here. There's a bigger one and a smaller one in this particular case. So this dude's making chill water, doing his thing over here. This guy is making hot water in this example, and there's piping between the 2 of them. Right, that's the gray dotted lines. So this guy is designed for let's say it's wintertime. This guy is designed for the amount of cooling I need in the winter, and he's designed for the amount of heating that I need in the winter, perimeter zones, things like that. Right, but come summertime, I don't need hardly any heat in this case. Forget about domestic water in this scenario. This is just a heating building, right? I don't need any heating in the building, but I do need more cooling. Instead of having 2 chillers here, this heating chiller can become my other cooling chiller, right? And these valves can open, and now basically this water loop is off, circulators are off. I don't send any hot water out to the building, but the chill water can flow through this machine, and it can go up this way, up the gray line, and flow through the other chiller with the reversing valve flipped to cooling mode and come back in. So now I can have these 2 chillers working in parallel for cooling mode, and then come heating season, it can flip, and it can be back to the opposite. And if I need a ton of heating, and I don't need any cooling because it's a smaller building, I can make both of these guys run in heat. So wintertime, I can have 2 machines running heat. Summertime, I can have 2 machines running cooling. And in the spring and fall, I can have one doing heat, one doing cooling. Because maybe the east side needs heating in the afternoon, but the west side is going to be beat on by the sun and they need cooling, right? Something like that. On the heating loop, I can also have supplemental heaters on there. Now, if I sized everything for 110 degree water or whatever, I might not need this. But if the building's existing and I was expecting 180 degree water to all the heating devices, and I don't want to change out all the heating devices, but I do want to do the heat pump chiller, then what I can do is I can have an additional heater that supplements this loop. In this case, there's a gas-fired boiler that's dumping heat into this loop. That would be probably for your guys' climate, that'd be the most efficient way to do it. You could use an electric boiler because someone says, I want to have an all-electric building. But in that case, you probably really want to think about, should we spend more money to put in bigger coils and radiators instead of getting this ginormous electric boiler? Because that would be pretty rough to make 180 degree water with electric boiler for the whole building. But in any case, you could choose whatever heating source you want: gas-fired boiler, condensing boiler, inefficient boiler, electric boiler, waste heat off of some kind of process, whatever you got to dump heat into this loop. And that's actually the machine that was shown in this one. Okay, I'm going to apologize. I'm going to put these back the order I had them because I'm dumb. So I should have gave you that one. Yes, I'd like that. Continue. Okay, so I should have showed you that one, then explain these, and then we'd have been here showing you that machine that was in there. By the way, for my day job, Trane is my company's competitor, and I'm just using their slide. So A, I'm recognizing them for letting me steal their slide, even though they don't know I did that. And B, don't tell any of my coworkers I did that because they'll be pretty pissed that I used a Trane slide. But it was kind of a nice slide. It was a specific machine that they had, but I like down here because it was specifying out what this thing can do. This particular machine, which is the one that was used in this example here, this particular machine can make chill water from 40 to 65 degrees. Great, that's exactly what I need at these types of outdoor air conditions, exactly what most buildings need. And it can make hot water up to 140 degrees, which is what I need for most jobs, not every job. So it can make me 140 degree water, on a 0 degree day. So that's very helpful in this regard. Show these temperatures on here. You can get, for not just this manufacturer, but many, you can get the pumps built into some of these machines as well. In terms of operation hours, obviously this chart would be different depending on your project. But we're showing here is percentage of run hours over the course of a year, 8,670 hours a year, whatever it is. So this is this machine in this example here, right? Where I got two machines, one set up for heating, one set up for cooling, but they could help each other out, right? So that's this scenario here. So how often do I need both heat pump chillers running cooling, right? It's, you know, whatever this is, 3% plus 1%, 4% of the year, or actually, no, sorry. 2 heat pump cooling, 13%, but those don't add up to 13% visually. Oh, because there's in between 96, 97, 98, 99. Okay, when I add them all together, this is just showing the temperatures like from a visual standpoint, but there's each 1 degree block in there. All right, so 13% of the year, I need both machines running cooling. 33% of the year, I need one machine running cooling and the other one's off. 5% of the year, I needed 2 machines running heat. 46% of the year, I need 1 machine running heat, and the cooling ones are the other machines off. And then in the middle, 3% is when I would have needed a heat recovery in this application. So some buildings need a lot of heat recovery. Like, remember I said, if you have a lot of domestic water, hotel, laundry, showering, condo buildings, swimming pools, those kind of things. Then there's other buildings like an office building where you don't have a lot of time that I need both simultaneously. There is some, so it becomes less interesting because you don't use a lot of domestic water on an office building. So in that case, it might be smarter to have these 2 machines piped like this, where they can both run heating or both run cooling. So there's a lot of variables on what we can do with all these chillers. I mentioned the water source heat pump earlier, right? So each individual tenant area or zone gets a water source heat pump, which is basically like a little baby water to air chiller, right? So it's taking water off of a water loop from a cooling tower historically. It's getting 85-degree water from a cooling tower. It's dumping heat from that zone into the water, sending 95 back out to the cooling tower to be cooled. So there's a refrigerant to water heat exchanger in here. Each of these machines has this heat exchanger, and they have a compressor in there. And then they have on the air side, they have a refrigerant to air heat exchanger. Some of these zones are in blue are showing that they need cooling. Other zones are needing heating, and they're dumping water onto the loop. This exact machine is the exact same thing we're doing with these chillers. But in this case, when it's a water source heat pump, that usually implies we're doing it on a zone by zone level. And there's a water loop running around the building. When it's a heat pump chiller or a heat reclaim chiller, it's implying I'm doing it at the building level. And this machine, there's one machine in the central plant being switched over. You can also do this stuff with geothermal. So geothermal system is a water source heat pump. It's not anything different, right? It's obviously being set up differently and piped a little differently, but it's the same idea, right? It's a water source heat pump. Instead of sending its heat into a cooling tower, it sends its heat into the ground in the summer. So no cooling tower on the roof typically. He sends all the heat into the ground. The ground cools off my water and sends it back. And as I'm doing that all summer long, guess what happens to the ground temperature? The ground starts heating up. By the way, in most areas, when you get below the frost line, the ground temperature doesn't change throughout the year, unless you have like an aquifer flowing water through it or something weird like that. But other than that, once you get below the frost line, the ground temperature pretty much is almost the same year round. So, but if I got a geothermal heat pump dumping heat into the ground all summer, the ground gets warmer and warmer and warmer, which is great. I'm cooling off my water. I'm doing it without running a cooling tower. Then come winter time, when the heat pumps start flipping over into the heating mode, now those heat pumps can pull heat out of the ground, and not just the fact that the ground temperature, was started out at 60 degrees or whatever it was, but now it's starting at 80 degrees because I banked heat there all summer long. So in the summertime, you're banking heat in the ground. The ground is basically a ginormous storage tank for heat. I bank it there all summer, and in the wintertime, I take it back out, right? It's a pretty cool idea. When you do this, if you're on an annual, and zones can be, the geothermal heat pumps for these zones, some can be running heat, some can be running cooling at the exact same time, just like the other water source units did, right? And some are dumping heat, some are taking it out. But on an annual basis, if I put as much heat into the ground as I take out, that would be awesome. Like it'd be the perfect storm scenario. And I would not need any other heating and cooling sources. I would just have these geo units, dump heat to the ground, take heat out of the ground, right? However, it's very unlikely you put the exact same amount of BTUs in the ground as you take out of the ground. So one of those seasons is typically more dominant. Let's say you're cooling dominant. You're shoving more heat into the ground all year than you're taking back out the rest of the year. Well, then come next summertime, instead of starting out with 60-degree ground temp and heating it up to 80 over the course of the summer, now I'm starting at 62-degree ground temp, heating it up to 82 over the course of the summer. And then the next year and the next year. And then eventually at some point it's too warm. It becomes a problem, right? Or vice versa. Let's say, and this is more common for where we live, we're taking more heat out of the ground in the wintertime. So instead of starting the season with 70-some degree ground temperature, I'm starting with 60-something. And the next season, I'm starting with 58. The next season, I'm starting with 56 because I'm taking more out of the ground than I'm replacing in the summertime. So what happens in these scenarios is whatever one is more dominant, I need something to take care of the rest. So let's say it's a heating dominated building. That means I'm going to have this ground loop and I'm going to have a small boiler there, gas fired or electric, a small boiler that is going to be supplementing this loop. So when it gets to the point of the winter, typically later in the winter, January, February, and the ground temp's not doing as good of a job because they don't have as much heat stored in the ground, the boiler will kick on to temper that water up a little bit more. If I did have a cooling dominated building, then I wouldn't need that boiler. Instead, I would have a supplemental cooling tower. I'm shoving more heat in the ground in the winter than I'm taking out in the summer. I need a cooling tower to trim off that difference. And maybe the cooling tower doesn't have to run in June, but maybe it does have to run in September, right? So the same idea that I have with these water source heat pump jobs being coupled to geothermal loops, I could also do that with a chiller. So instead of having water source heat pumps in all the individual tenant areas, I could have fan coils and air handlers in the tenant areas like a normal building would have. And then in the penthouse, or in this case, probably more likely in the basement, I would have my geothermal chillers. And those chillers would be sending water to the ground, condenser water in the summertime. And then in the wintertime, that water would be, we still call it the condenser water actually, but it'd be my warm water. It would be my evaporator water, but no one says that. And I am then afforded the ability to have a pretty efficient system. Geothermal is one of the most efficient things you can do. Water-cooled chillers are really efficient. And when I combine those two things together, I can get some really sick efficiencies, which is phenomenal. This is a piping diagram that I did when we first started conceptualizing this at my office. This is from 2008, I think, is how long ago this was. Before that, we didn't really do this. And we don't do it a lot, honestly. It's a rarity, but you can do it. In this case, I have 3 fan coil air handlers on here. It could be 3, it could be 300, right? But from a drawing standpoint, you can't put everything on here. So I put 3 of them on here, and I only showed 1 chiller, but you could have 2 of them, and that's more likely as well. But this is just showing 1. Here is all the things that I talked about before. I got my expansion system, my air separator, my circulating pumps over here, right? Going back to I lost my mouse. What the heck? Slides loading. What does that mean? Give me 1 second. Good. PowerPoint locked up. Restart or close the program. Those choices suck. Okay. Restart the program. While that's restarting PowerPoint, I will read the question that just came in from Clark. Launch PowerPoint. I won't read the question that came in from Clark. You want to recover this? No, I don't. Go back to my slide. Sorry, guys. 1 more second. Okay, PowerPoint is recovered. Clark says, since the incoming domestic water service is stable temp year-round, can it be used for water source heat pump like geothermal? If so, what volume makes it effective? Does that line up with the domestic water use? Okay, a couple things you could be talking about. So if you were talking about that when this slide came up, which you might have been, these water source heat pumps are being connected to a cooling tower and a boiler typically on most buildings. You could connect them to the domestic water. A lot of times that's called a pump and dump system. You run the domestic water from the city water through there, run it through the heat pump, add heat to it or take heat out of it, and then dump the water down the drain. There are buildings that do that. There's nothing that does that that's been built in the past like 30 plus years. That's no longer allowed by any codes, but there are still buildings that have it because that's what they had from day one. And it's some big giant building, and there's not really any good way to add a cooling tower and a boiler to it. So you're just basically dumping water down the drain. It's super wasteful for water, but that does exist. So if you're talking about that, yes, you might run into one of those buildings where you're using city water to run it through the coil on the water source heat pump, but you won't be designing one that way. If I read your question again, domestic water sources can be used to the water source heat pump like geothermal. I'm not quite sure what else you could mean. Were you talking about a pump and dump system, Clark? Or were you talking about something over here? And instead of having this, you want to use... So you either would use the domestic water to pump and dump it, or you'd be doing, like I said before, with the heat reclaim chiller, which was one of these guys. Your domestic water is this water load. Mark says, let's finish Clark's question. Not pump and dump, just like geothermal. Okay, so use the city water instead of the ground temperature. But then where do you send that city water, Clark? Do you send it to a cooling tower and a boiler? Or do you send it into the drain? If you send it into the drain, that's a pump and dump, can't do it anymore. If you take that domestic water, add heat to it or remove heat from it, and then send it to a cooling tower or a boiler to be heated up or cooled down again, and that's what we were talking about earlier. Those would be the three scenarios. Geothermal loop, taking the city water in and then making it your water and coupling it to a cooling tower and a boiler, or dumping it down the drain. Those are the only three places I could think of that you would send it to. Mark was saying, I'm surprised that you say there's a year-round increase in ground temp. I would think the earth is a huge sink and would in time dissipate the heat. Is the increase you mentioned significant or tiny? It is significant. It's enough that we have buildings that early on in the geo days were not designed with that thought in mind. And then over the course of, say, 5 years later, they no longer can heat the building with just the geo. The groundwater temperature is too cool, and they have to have a supplemental heat source added to the building, like a boiler or electric heaters. So it is pretty significant. It is, can be 10, 15 degrees. It depends on where you're at, what kind of ground you have. If you have a lot of stationary ground, like thick granite and stuff like that, which I think you guys actually do out in the Northeast, then the ground temperature is pretty consistent. If you have ground that like you're in like the central, like Tennessee and stuff like that, or if you're like really far, like if you're like down in Florida or Louisiana where it's like a swamp, there's so much groundwater moving that you would not have this problem because you have heat being moved by the water moving underground. But if your ground is stationary, it's like a storage battery. You're just heating up that granite, you're heating it, or whatever ground you have, you're heating it, heating it. And it takes so long for heat to move from rock to rock to rock underground that it would take years to dissipate all that heat. So you are degrading the temperature of the ground when you don't have a balanced load on a looped geothermal system where the ground is pretty hard material. All right, let's see. I think another question might have come in. Clark's back on his using domestic water. It gets used constantly for the building sink. If you're using domestic water constantly, domestic water means I have water coming in from the city and then going on a sink. If you were doing that, that's the example we showed before. That's these heat recovery machines. That's what these are. This is domestic water in most applications right here. So I would send domestic water through this. Or this could be a heat exchanger and the domestic water is going to the heat exchanger and then this water is going. Either way it could be. But domestic water would be this scenario. Let's see. Clark added something to Mark's question. Scandinavia is putting pump loops in roads to groundwater and heating up the water table, tapping in water for buildings and road melt simultaneously. So you're using it for snow melt on the road. That would be okay as long as the building you're coupling it to needs cooling in the wintertime. Then you could do that, obviously. And that would be a pretty good idea because you don't need crazy hot water temperatures to melt snow. You can melt snow with 100-degree water going through the loop. It's faster if you send it warmer water, obviously. You should change the GPM. But yeah, if you have a building that needs cooling in the winter, and out in front of the building you have, let's say it's a hospital and you do need cooling in the winter, right? Even in Scandinavia, you probably need cooling in the hospital in the winter, operating rooms and stuff like that. But then out in front, you have the drop off for the emergency room, and you want to snow melt that because you don't want people slipping when they go into the emergency room. And then maybe you got a helipad and you want to snow melt the helipad. You could take the heat from your building when you're running your chiller, your heat reclaim chiller, and send the waste heat to the snow melt and to the helipad and melt the snow on those. You could definitely do that. That would be cool. Mark saying that it's interesting that it makes sense that what the ground is made out of will make a difference on how long the heat stays in the ground, right? The density of it and whether there's water in there that can move. Yep. Paul has a question. Couldn't the bore field for geothermal be designed for extra depth of bores to allow the energy to dissipate and have more constant year-round temperature? Yes. Okay, so you could do that. So what Paul is suggesting or asking is that here, maybe instead of putting in 10 wells, I put in 30 wells in the ground. And now I have so much volume of ground that I could put all my heat into the ground and take all my heat out of the ground and not worry about, the over conditioning of the ground like I did before. The problem with that is now I'm paying for 30 wells instead of 10 wells. And that's really expensive. It might be better just to pay for the 10 wells, the baseline, and then have a small boiler tempering the rest of the way, right? Or a cooling tower if the problem was the opposite way. But yeah, you can just keep making the geo field bigger and bigger and bigger and bigger until, then instead of heating the ground up a couple degrees a year over the course of the year, plus a couple degrees the next year and a couple degrees next year, you're heating it up, tenths of a degree over the course of a decade, and it doesn't matter then. Yeah, you could definitely make the bore fields bigger or put more of them in, but now you just need more space, more drilling costs, and most people have taken the choice of balancing that off and saying, nah, let's just do the base amount of wells, which means you do the amount of wells it takes for the smaller load of the heating and cooling. Whichever one's smaller, you put in enough of a well field for that. And then your other heating source or other cooling source takes care of the gap between those. That's more common because it's a better first cost standpoint. And you get almost all the energy benefits of the geo, and you drop the first cost a lot. Mark asks, are you aware of the use of heat pumps on farms, like greenhouses, where they just need to heat in cold weather, 40 to 70 degrees, but no need for AC cooling in the summer? Is this practical? I'm not in the loop on any greenhouse applications for heat pumps. We do a fair amount of, we don't do a fair amount of greenhouses at my office, but we do a fair amount of grow facilities, which should be indoor marijuana growing. And that's a highly specialized industry. And we use all kinds of specialized equipment because the latent load is so high in most of those rooms that we use specialized equipment for that. But using geothermal, maybe you can use it for the baseline, but it'd be really tough to use it for a whole entire building for a greenhouse, because even though you don't need cooling, most of those facilities are going to want to do dehumidification. Unless it's like an old school greenhouse where they're just going to have all the windows open and completely ventilate it, and they're not going to grow in the winter. But around where I live, anything growing indoors, they're doing it because they want to grow 12 months out of the year. So everything we don't really have greenhouses. We have indoor grow buildings. But yeah, I don't know about that one, how practical it would be. In terms of using them on farms, that actually, in general, that's pretty common. But like residential, like homes on a farm, for example, my wife's from the farming community, and when we go down and visit her family, two of her family members, her uncle and her cousin, both have geothermal systems. Right. And it was kind of funny because they know I'm in HVAC. So I'm over there and they're like, hey, you want to come see my new system? I'm like, yeah, I'm a dork. That's exactly what I want to do. And we go in the basement. I'm like, dude, you got geothermal? And they're like, yeah. Like, dude, it's awesome. Like I dug the well, they're farmers, right? So they got backhoes and stuff. I dug the horizontal field. I laid the tube, I grounded it, I put the tube in, and then I had the HVAC guy come in and do the hard part inside. I'm like, the inside was the hard part, the sheet metal, not digging all this ground loop. And because they're farmers, it's easy for them. They already have the equipment. But the nice thing about doing geothermal in a rural area is you don't need vertical wells like this. Like where I live, like if you did residential geothermal, you got to dig a well. I live in suburbia. You got to dig a well 175, 225 feet down. Literally no one I know has geothermal, because where I live in suburbia, nobody has a well, or nobody has a rig to dig a well, because we don't have well water here. So no one has a rig. So you got to have a rig come in from 3 hours away to dig your well. And it just costs too much to do that. But you go somewhere rural, not only do they not have to go vertical, they can go horizontal, which means you don't need a rig to dig a deep well. You just have to dig a 20-foot deep trench, which you can do with almost any farm piece of equipment. So you can have it go horizontal trenches for geo. You can go vertical bore fields. You could have a reasonably deep pond where you put a coil in the pond. You could do it with river water. You can stick a coil in the river water, or you can just use river water directly. We have some projects like that in downtown Chicago, where there's buildings right on the river, and they have a permit from the EPA to suck river water into the basement of the building, run it through the condenser side of the chiller, and then dump it right back into the river. I think the EPA only gives so many of those permits because now you're warming up the water temperature of the river over the course of time, which obviously changes the way things are for fish and stuff like that. All right, let's get back on track here. I thought we were going to be done early, but good questions. All right, so we were on this before I started the questions, which I'm not complaining about the questions. Love me some questions. Let me clear these questions off so I can see if a new one comes in. We got them all. Answer. And by the way, thanks for everybody who's also throwing ideas and not just questions. That's cool too. Okay, so we were talking about this guy. We only got a couple slides here. I think 2 more slides. So indoor air handlers or fan coils, all my hydronic stuff that I need there, air separator, expansion tanks, pumping systems. And then on the other, dude, laser pointer, killing me, Smalls. Okay. Dude, for whatever reason, this PowerPoint keeps locking up on this slide on me. Hopefully you can still see this right now while the PowerPoint's got the little swirly locked up thing. So I'm going to go ahead and just keep talking about it until the PowerPoint crashes. On the other side of the chiller, I have these other water loops, which has its own pumping system and its own air separating expansion tank, because this water loop doesn't touch this water loop, right? At least not initially. And then I send that down to the geofield. Instead of having reversing valves in the chiller, before we had those kind of chillers, we could put reversing valves on the water. It's not as easy. Instead of 1 reversing valve in the refrigerant pipe, I needed 1, 2, 3, 4 on the water valves. Dude, come on. Restart PowerPoint. Damn it. I needed reversing valves on the water side. So I would take the water from outside and reroute it to the evaporator side. Where'd it go? Reroute to the evaporator side, and then take the indoor water and route it to the other side. So you can do it that way as well. It's a little more costly on the install side, but it allows you more flexibility of the types of chillers that you could have utilized to do it. So that's one drawing that we had done years ago. And then here's one that's kind of similar that some of my competitors had done, right? Where they got 1 water loop down here doing cooling, 1 doing heating, and then they have a separate heat source, which could be a boiler or chiller, supplementing the difference, or geothermal loop, or whatever it is. All right, more questions. Alberto said, let everybody know about the email letter coming out. So Alberto at UMass is going to send an email out to you guys regarding the CEU certificates. It'll come from Alberto at UMass, but it'll be the Massachusetts MAEEP, Massachusetts Energy Efficiency Partnership. So between them and UMass does all the training for them, obviously, which is Alberto's side of the equation. So watch that in your email. So I'll send you an email that has the link to today for those that you wanted that. And then Alberto will also be having sent out to you the CEU email. We have 3 minutes of anything else anybody wants to ask. Jason said, great training. Awesome. Thank you. Appreciate it. If you guys have other topics you want in the future, you can send them back to me on one of the emails, reply back to it, or you can send it to Alberto. And even if it's not something that I'm good at, I usually talk to Alberto a couple times a year and, hey, I can do these topics. Hey, I can't do those. Here's a guy that might be able to do those. Or sometimes I have nobody and he has to go find him somewhere else. But they do a good job of finding different speakers on different topics. So any ideas you have, I know Alberto loves to hear them as well. So send them to me or him, and we'll just share them with each other. More questions or anything? Cool. Well, I thank you guys for your time. That completes all 5 modules. Believe it or not, a couple people suggested doing this as one long 8-hour class online. We have it as a full class in person, but online would be pretty tough. So I think it works out better this way. We're taking little 1.5-hour chunks. But I know it's harder for everybody's schedule, which is why we record them. So everybody should hopefully be good. All right. Thank you guys for your time. And I'll see you the next time Alberto has me in town. Since I'm still on and some of you are still on, just throw a couple other things out there. Amar wrote in, Iceland uses geothermal energy for heat and electric. So that's my fault. I called it geothermal. It's ground source heat pumps. Most people call a ground source heat pump a geothermal heat pump because they think you're getting energy from the earth, which you are not. You are just banking it there and taking it back out. True geothermal, like Amar is talking about, like they use in Iceland, that's where you have they have like geysers, like Old Faithful type energy under the ground, and you literally are taking heat out of the ground in those cases. So that's a totally different scenario, and only certain areas can do that, obviously. Iceland definitely is one of those areas where they have tons of geothermal energy, get all those natural hot springs and all that stuff. Yeah, they can actually take heat out of the ground and use it to heat buildings. And like he mentioned here, you can also run it through turbines and generate electrical power. Very cool, Amar. That's awesome stuff. And I apologize. I usually am pretty good about clarifying geothermal heat pumps versus ground source heat pumps, but literally everyone in my office calls it geothermal when it's not. Cool. Mark just added some extra thoughts. Because he said not to respond, but I can't. My body has to respond to everything all the time. Said that they have used some heat pumps in farmhouses and small human occupied spaces. And I think he was asking, just if I seen any like larger scale stuff. But it's pretty cool. All right, I really am